Welcome everyone at my talk. Nice to hear you at all, because I'm pretty sure and conscious about how usually people feel after party at the conference. So I'm very glad that any one of you came here. Okay, just as a survey, how many of you were present yesterday and were listening to the other talks regarding stream gatherers? Hands up. Oh, not so bad, only half of the audience. Still good. For all of you that have raised your hands up, you will feel that like consuming dumplings being recooked 3 times, but I try to present it from a little bit different angle, so I hope that you will also be a little bit glad. Thanks very much. So, not to waste time, because we had a lot of code to being presented during the talk. I try to share with you a lot of examples of the stream gatherers and how do they build, especially the custom ones. Let's start from a very simple task that you are usually usually do it on your daily basis, and it's just imagine that you have in your code a collection of cars. Each car is being represented by 2 properties. The first one is a brand, and the second one is a color, more or less. And we would like to select only that cars that are distinct. So we do not want to return to the consumer repeating cars. Okay, they should be distinct. So how to accomplish that? It should be relatively easy, but let's just jump into the IntelliJ for starting just from the beginning. Let's check out how it looks like. So as you can see, we have this record representing cars, exactly this one, okay? It's model and color. Model is represented by string, color is an enum. We have only 3 values, red, black, white, sorry. My sense of colors does not detect any others, so it should be enough. And we have a list of cars, the 5 ones. These brands and colors are more or less the cars I have possessed in my life. So not too wide list and not too expensive one, as you can see. And I would like just to select distinct cars. So the solution is pretty straightforward. Just run this stream and just use the operator distinct, put this into a list and print it with this. And if we run this code, as you can see, exactly we have 4 cars. So it's what we have expected. Nice. So we can sum it up as a piece of cake. It's relatively pretty straightforward, there is no problem. So, being somehow forced by this very simple task, let's go to another one. Yeah. Select cars, okay, but with distinct colors. So, we do not want to repeat in the outcome the cars that have repeating colors. So, seems relatively not so bad. So let's jump into the code once again. Okay. On purpose, I omitted the solution because we can somehow think how to solve that. Okay, we will start from the just using this operator stream. So, okay, return cars stream, because this is the simple part. And now we have a lot of problems because unfortunately doesn't work and doesn't compile. And it's also very interesting why. Okay, because it's a return. So let's don't do this one. Okay, car stream, and now what to do down here? Distinct will not help us because distinct works only on the full objects and compares it by its equals method. So it isn't what we want to achieve. Okay. Do we have any other operator, distinct by color, distinct by key, and so on? Of course we do not. If you just try to find it, it's okay. It's only distinct. Okay, it doesn't help us. So maybe we should go that way. Car color. Nice, okay, we are just mapping this car to the color. We can also somehow transform it to the method reference, but still that does not make any difference. And then we have a problem, because unfortunately, if we use this mapper, the stream of car changes to the stream of color. So how we can restore the original object if we just lost the information about the rest of the properties except the color? Does not work at all. And it seems that we are somehow stuck inside this code. So is there any solution? Of course it is, because I wouldn't dare to show it until it's working. So the solution looks like that. We need to prepare a map and collect these cars to a map using the color as a key mapper and value mapper and merge function to just skip another car with the same color. As you can also see, these examples nicely show another small feature introduced in the new version of Java, as far as I know, 22. It's the unknown parameter in lambdas and also in catch clauses, which represents us the variable we do not want. Sorry, I don't show that. We do not want to somehow name it because usually naming variables in programming consumes most of our time. So if we can omit it, it's fine. But summing it up, this solution to the relatively simple problem is relatively overcomplicated. Why does it go? And what's wrong with there? Because it's holy cow. And when we are looking about this solution with the map, only I can say is, what? Sorry, it shouldn't go that way. So let's somehow try to discover how this problem and many others can be solved in a much more simpler way, introduced in Java 24. My name is Marcin Chrost. I'm working in C and dedicated to Allegro project in Poland, and also I'm conducting a lot of trainings, cooperating with companies like Bottega, IT Minds, and J Systems. If you are interested in what I offer and my trainings and my other things like my GitHub, you can just visit my page chrost.eu and say widely recommend to that, but not to waste a lot of time for this slide. Let's go one step further. If you also have questions for the talk, you can ask them in parallel to my presentations. Just go to the app Slido, select the hashtag GeeCON, and select do remember room 12. Okay, let's go further. We are just thinking about elastic architecture because the question is why this operator distinct by key or something like that hadn't been added to the Java Stream API. It comes from the what we say elastic architecture. And if you are interested in such topics, usually most of all, if not all, most of you are not all, knows the solid principles, the design principles of object-oriented programming. And in this mnemonic, the O stands for open-closed principle, means that open chest surgery isn't needed when putting on the code, and to transvesting into the software development principles, the classes should be open for extension but closed for modification. So if you just want to add some new behavior to the class, you shouldn't change its implementation. You should invent something that is more flexible and allows you to extend the behavior, but without modifying the class, more or less. So definitely the architecture should be elastic. Of course, not that way. I just noticed it yesterday in my apartment on Booking, because this is very elastic, but let's go not far beyond, because, okay, you can connect any electric device using these cables, but no, it shouldn't be. This I in mnemonic, the interface segregation principle, it's definitely also being done on purpose, but let's go further. So it means that adding these new operators to the Stream API definitely breaks the open-closed principle, and it means that we should go a little bit different way, and this is the reason why this hasn't been added. So now, after this brief introduction, we can introduce something like gatherers, stream gatherers, but I will also use the shortcut because it somehow saves the time. So What is stream gatherers? Probably you are already conscious about it after yesterday's talks, but just as a quick reminder, they have been introduced in JDK 22 as a preview feature, and fortunately in JDK 24 they have been added as a permanent. It's fine, because usually in the world of Java development, adding something like a permanent feature should be celebrated as a holiday or even a festival, because usually a lot of things like string patterns hasn't been added at all, and many others like structured concurrency is still not being added as a permanent feature, and we are waiting like for a Godot, unfortunately. But stream gatherers, the situation is just pretty straightforward. I can only somehow talk that it has been relatively quickly selected as a last pope on Conclave. 2 days and everything is fine. Nice. I would definitely like this processing also with Java community. Okay, but let's go further. And stream gatherers allow stream advanced grouping and processing, and we will talk about it later on, a few slides later. And in my opinion, this is the missing part of the original Stream API added to JDK 8. Because it complements what is missing, and with the stream gatherers, definitely all of parts of this processing stream is now being able to achieve. Okay, as a quick recap, let's look at the quick overview of the Java Stream API, because if the Java Stream API, usually we have 3 parts, and the intermediate one is optional one. However, the first and the last are the mandatory. So definitely, when we are working with the Stream API, at the first point, we have to somehow create the stream, because if we do not create it, we can work on it. So usually it's being done by the stream operator on some collection of arrays, but if you do need it more programmatically, or you need to customize it, you have these classes like stream support and splitterator, so you are not bound to the stream operator as such, and then you can construct your stream as you wish. Okay. Let's skip the intermediate operation for a little bit. Let's go to the terminal one, because the terminal operation, on the other hand, is the one required for any stream to just run, because stream API is a lazy one, and if you do not connect the terminal operations, nothing happens, nor the stream is created, neither the stream is created, nor the intermediate operations took place. But in the terminal operations, of course, we have a lot of them, for each, find first and image, and so on and so on. But if any of them doesn't fit the bill, you can still use the collect operator and write your custom collector. So in this case, you are also not bound to what the Stream API offers you, and you can extend it your way. And then the most problematic part, and the most important in my opinion, are the intermediate operations, because you had a lot of them. Map, filter, distinct, sorted, and so on and so on. However, finally we come to the fact that we need something equivalent to the stream support on the beginning and the collect on the terminal at the end. And this part, this programmatic way to implement these intermediate operations is gather, and this is being added in Java 24, and this is a part of the stream gatherers. Okay, how does it look like? Because when we are thinking about gatherer, this small piece of logic looks relatively small, but it's not so easy as it seems, because such gatherer needs to somehow implement relatively complex logic. Because in such case of this piece of puzzle, you need to somehow be able to consume up to n elements, and afterwards push another number of elements, because in this picture it's a little bit, there is a small bug, because on the left side should be not m but m, because it would somehow better present the number of elements being pushed and be to the gatherer, and being pushed by the gatherer to the downstream may be different. It's a very crucial part of this topic, but let's go later on. And as you can also see, this gatherer is somehow working in the push mode, which can be somehow counterintuitive, because usually people working with the Stream API think that it's working on the pull basis, that the terminal operations pulls the elements from the stream, but it's not completely true. If you somehow deep dive into the Stream API, especially in the reference pipeline class, you will detect that the Stream API behind the scenes work in the push mode, and the elements are being pushed from the splitterator on stream support through the something like called sync to the downstream. And exactly gatherer works in this model. Also adding some other factor is being the downstream check whether it can accept elements or not. And you can see gatherer is pushing the elements to downstream, and downstream can at any time reject any other elements and say, stop, I do not accept them, please do not push me anything more, that the stream is finished. Okay, nice. So, what do we have as a built-in ones? Because the gatherers API is a little bit, maybe not complicated, but requires a few steps to create your own custom gatherer, and we will do it in the later part of the talk. However, it also comes with the built-in ones, and initially there are 5 of them. I will try to explain deeply 2, and we will start from something like scan. I borrowed this picture from the Reactor API, from the Flux class, because in my opinion it best describes how the scan gatherer works. And scan gatherer works exactly that way, that it's consuming the elements from the upstream, and after consuming each element, it does the binary operations, do something with the result, and also adds when the next element is also arriving, it repeats the operations to the next element, and so on and so on. In this diagram, it seems that this operation is just adding some layer of cycles to the score. In the real examples, you can also think about the scan operators, like using for add some, make a sum of elements, and so on. However, it's not only this application of that, and I will try to show you how the scan gatherer works in a little bit different way when we are trying to find the local minimum and maximum of elements in stream. Let's go to the IntelliJ and present this example. Okay, current min-max. Okay, let's go that way. Assume that we have a stream of numbers. If you look deeply into these numbers, is just the digits of the p, the first digits of the p number, but not the focus about it now. And what we want to achieve is the local minimum and maximum at the certain point of the stream. So we want to know, after each element, what was the minimum element up to this point and the maximum one. How we can achieve it with the gatherer, the scan gatherer? It's very simple. We present, of course, to achieve that, we need a structure that stores the minimum and maximum element at this moment, and we enclose it in a record, min-max. And the names of its properties are just self-clarifying, so we do not focus on that. And then scan gatherer has 2 lambdas that you need to put inside it to work. The initial lambda prepares the state of the gatherer before any element appears in the stream. And this, in such case, we are just using this algorithm of with sentinels. So our max and min values, especially you can see that they are being put into the record exactly in the opposite way. So for the min field, we are putting the max value. For the max field, we are putting the min because we will be comparing with that. So definitely everything is less than max value and bigger than the min one. Okay, let's go. But the main logic of this gatherer is being contained in the second lambda. And the second lambda is being called for every item appearing in the stream. And in this scanner, we see that the lambda also is being provided with two values. The first one is the current state, and this is the min-max. We are just created before any element appeared. And the second one is the actual value of inside the stream. And now the logic is pretty straightforward. We are just calculating the minimum and the maximum value, taking into account our state. It's very relatively easy. And then we are returning the new state, the new item of the stream. As you can see, this scan gatherer results in stream which elements are these state items, min and max. And for each, now we are printing it on the output. And as you can see, it should exactly do what we expect from it. So it's calculating the local minimum and maximum. For the first element, it's pretty straightforward that both of them will be equal to the first element, but then the situation starts to clarifying. So the minimum is just set to 1, and there is no lower element than this one. So the minimum stays until the end, and the max is being constantly raised up to the 9 value. Okay, fine. That's all. Let's go to another built-in gatherer. Okay, let's go here. Okay, Another one I would like to talk about is the window sliding. Probably all of you know this kind of algorithm when we are trying to analyze some piece of elements of the stream of the certain size, and we are analyzing them step by step. So we, for example, want to analyze 3 items in the whole stream. So we are just creating the window on the first 3, and then after performing some calculations and so on, we are sliding the window by 1 element, and then repeat the algorithm for the next slide. So. And always this sliding window has the same size, so we are just using it to perform some calculations. Some examples of that are, for example, noise smoothing, detecting some abnormal values in the stream and silencing it, and so on. But in my case, I would like to present you this sliding window algorithm for another example, just trying to find a matching pattern in the stream. How can it look like? So let's go to our IntelliJ once again. And okay, 0.3 pattern matching. Okay, this is relatively a quick example because we have a list of elements, only the binary ones, just to somehow make this more interesting. And we would like to find where, if in the list we can spot a pattern consisting of 3 elements, 1, 0, 1. As you can see on the first glance, there are 2 of them, at the index 0 and the index of 3. As you can, there is only what we can find. But with the gatherer window sliding, finding it is relatively easy. You are just creating a gatherer of this window equal to this pattern length of 3. Also, somehow it should be replaced with the pattern length, but it's fine. And then we are sliding step by step and comparing whether this current window equals to the pattern. And if it equals, we are just for each printing this pattern found example. Okay, if you run this code, we can see that this pattern is found 2 times, but you can ask very important questions. Okay, fine, but this information is 100% correct, and it's 100% useless because you do not get an index of the pattern when it has been found. And to accomplish this another requirement, which in my opinion is relatively important and needed in such situations, we need to somehow change the gatherers. And to change the gatherers, we need to implement, reuse the scan one. So let's go to the another example. It's 04. And with this pattern, we need to somehow make some preparations, because when we are comparing these elements of our list, we need to know at which index we currently are. And this is the place when the scan gatherer comes back into place. It's the return of the scan gatherer. So we definitely prepare a special index, record index value, and in this record we are just keeping only index and the value of the element in the list, and then we transform this list into the stream of the index values. And you can see initial initial operations, we are just setting the index to -1. It's completely makes no sense, but it's not being used at all. And after each element, we are just putting this index to the incrementing by 1 and adding the value. So after this, all these operations and at this stage, we get a stream of indexed values, and each index value contains the index of the original stream and then the value. Okay, and then we can just use back again the window sliding gatherer. Now it's fine, and we are filtering it by this comparing the value of the index value to the pattern. And after that, we are finally are able to not only find the patterns and also the index of that. So if you run this code, now we should find that these two patterns are being found in the index 0 and 3, which is what we exactly wanted to accomplish with the code. Okay, nice. Do we have any other built-in gatherers? Yes, that's true. I do not focus on them any, but let's try to mention it quickly. And the first one is fault, works exactly more or less like a scan, however, emits only the last item. So it's more or less the same as a reduce operator in the stream. However, the difference between fold and reduce is that the reduce is a terminal operation, so it just not allows to do anything. You just stop the stream and returns the value. Fold allows you to somehow connect any other operators, intermediate operations, and so on, because it's just emit the one value. This is just being folding the rest of the items in the stream, but allows you to connect any other operations, and this is in my opinion, the most important application of this operator. Okay, window fixed. And window fixed is somehow similar and somehow different to window sliding, because window fixed divides the stream into the windows of fixed size. However, they are disjuncted. So window fixed, for example, of the size of 3 prepares you the first window contains the first 3 elements, the second window contains the next 3, and so on and so on. And as you can expect, the last window probably may have the less elements as the original one. And that's all. And the third interesting stream gatherer is map concurrent. Sorry, I need to. And map concurrent allows you to perform some mapping concurrently using virtual threads. And that's very fine, because you probably heard it yesterday that the parallel stream and foreground pools was a $1 billion mistake. It does not work in parallel, and it's completely unpredictable. Map concurrent is a little bit better, because map concurrent allows you to perform some operations concurrently, and you can only on virtual threads, so it's also fine. It complements with the Java 21 virtual threads, and also allows you to set the level of concurrency and guarantees the order of the items at the end. So it's very fine operations, and you can use it in your calculations. But let's go to the raw meat, the custom gatherers, because as I can say previously, that the most important part of the gatherers is that you can write your custom ones and implement any operations you want. So let's start with this interface of gatherer, because we need to somehow deep dive in it, and it looks scary at the first glance. However, if you look deeply in this interface, you will notice that only one of this part is definitely the mandatory one, and it's integrator. And the rest is optional, and in many scenarios you can just use only the integrator, and it's completely fine. Also, the interface is a generic one, and unfortunately with 3 types, T, A, and R. T stands for the elements that comes into the gatherer. R is for the element that's being pushed to the downstream. A is the type of the intermediate state of gatherer, because if you are using the stateful one, we need to somehow store the state inside it. And also this applies to the integrator exactly the same way, but the order of the types of the generic is a little bit different. I don't know why it has been designed that way. Let's just put it on hold. Okay. And then, if we have initializer, integrator, combiner, and finisher, let's go to our diagram of architecture. And we will start only from the integrator part, because it's the only mandatory one, and integrator work exactly the same way I have presented a few slides before. It accepts up to n elements, do something with them, and produces up to m elements. And also, in case of, if we are talking about stateful gatherers, integrator also keeps the state of the gatherer inside it, and also mutates it, because state in the integrator and what it follows in gatherer is a mutable one. It's a very important way, and we will look into later on how does it look like with these things. Okay, so how we can implement a simple gatherer? We need to deep dive into the integrator interface, because as it is the mandatory one, we need to know how does it look like. However, fortunately, integrator interface only contains one mandatory method that you need to implement. It's integrate. As you can see, it accepts 3 elements: state, element, and downstream. And what you need in this integrator, you need to accept the element, check eventually the state, what is containing all, but if it's a stateless integrator and gatherer, you can just safely omit that. And then you need to somehow emit the elements. And for emitting elements, there is another functional interface downstream, and in this downstream interface, there is only one method, push. And with this push method, you just push the element downstream and forget about it. Why? Both of these methods return Boolean value. This is the part I presented a few slides before, because it represents the possibility of rejecting more elements downstream. So every time you push something to the downstream, you need to check what is the residual value of the pushing, because if downstream returns false, it means that you are forced to stop the process at all, not push any other elements inside it, and also return the false value from your integrate method to the upstream. So this this process of rejecting elements from the downstream propagates bubbles up to the source of the stream. And this is exactly more or less the way it should work. Having this said, the question is also how we create the instances of integrator, of gatherers. Of course, we can implement these interfaces and it should work, but fortunately, both of these classes, integrator and gatherers, have these factory static methods off, and with many other combinations. So we will try to present it in the very simple way. Let's start from the stateless gatherer. So we're not keep the state, we only just pumping the elements that are coming from the upstream to the downstream. And the first simple example of the stateless gatherer is a map not null. Let's show it that way. And map not null is just a gatherer that serves the purposes. The first one is just mapping the elements like the classical map, and the second one is skips the null elements that comes into this gatherer, so are not being pushed through the mapper, but just being omitted and skipped and not pushed downstream. How does it look like? As I can state previously, if you want to implement such gatherer, you can of course implement this interface, but there is fortunately a static method of. And this method allows you to pass different parts of this gatherer, so integrator, initializer, and so on, but as we are implementing the stateless gatherer, we need only pass the integrator and nothing else. And if we are talking about integrator, there are also two static methods, of and of greedy. We will talk about it later on, what's the difference between them. As now, you can assume that usually you should use this of greedy ones. This is also very funny thing in this integrator static methods, because the greedy is the default one and non-greedy should be the last resort, which is completely counterintuitive, but let's go. And now the only thing you need to pass to this of greedy is this callback, this lambda from the integrator. As you can see, this is state, so as is it void, because with stateless we can omit this safely and use just this underscore as an unnamed pattern. This is our item and this is our downstream. And what we only need to do is just when we are being executed our callback, we are checking whether this item is not equal to null. If it's not, we are just applying this mapper and pushing everything downstream. And in other case, we are just returning true. We are skipping the elements, not pushing the items, and say, okay, let's go. As you can also see, in case we are just pushing the element, we are directly returning what the downstream returns us. So if it rejects more elements, we are just also returning false, and nothing goes down. If we run this gatherer, as you can see, I prepared 3 elements on the list. I need to prepare it with the relatively old-fashioned way, because this list of static methods does not accept null at all at the list, so we need to do it with the array list from Java 5. As you can see, this gatherer exactly multiplies every item by 2, of course, assuming this isn't null. And this is exactly what we need to achieve. Okay, let's go one step further when we are talking about stream gatherers and the stateless ones, because I somehow introduced something like greedy. What's the problem with the greedy integrator, and what's the difference between the greedy and non-greedy ones? So let's come to our presentations back again. And what's the difference between of them? So greedy integrator, it should be considered the default one, may return false only if the downstream returns false. So it's being used only in case when it just propagates the rejecting signal from the downstream. So it means that greedy integrator is not allowed to reject elements on its own. It can only just use being run as a transmission belt from the downstream, and so on. Completely different story is with non-greedy ones, when constructed by this static method. Non-greedy integrators, when it's being connected to the stream, it's being assumed that non-greedy integrators may return false regardless of the downstream. So it can decide that, sorry buddy, I'm not accepting more elements, because due to my logic, I'm just stopping processing the stream. What case it is, and when we can apply such non-greedy integrator? Yes, the solution is very simple. Let's go to another example in code. And with the non-greedy integrator, we will employ it in this find first gatherer. And find first gatherer is a gatherer that we are trying to detect and emit only first element in stream that meets the given predicate. And the predicate, in such case, is being put as a element of this gatherer with its property, so we are passing in this constructor. As you can also see, gatherer, it's being typed with the same type as the input and output, because we are not transforming the items, we are only filtering it. Of course, it's being the middle item is void, because it's still the stateless one. We do not want to keep any state inside it. And our integrator, not greedy one, it works exactly that way. So we are preparing this item and the downstream, and we are testing whether the item meets the criteria put in the predicate. If yes, we are pushing it to the downstream, of course, because we need to push it, and then we are returning false. which means that we are stopping, not accepting many other elements, and the upstream we should stop passing us another ones. In any other case, when the predicate does not meet the element, we are returning true and waiting for the another one. And as you can see, with the examples of on our, we have the list of few numbers, and in case we are just trying to find the even ones, so we are checking whether the parity is being met, and in such case, we should only emit the first element of 2. So let's go. How does it look like? It's 2, so it works properly. And now we can present what's the difference between non-greedy and greedy integrators, because in such case, when we somehow our business logic may force us to end up the stream prematurely, using greedy integrator will not work correctly. In such case, when we run this code once again, even if we return false, we are still being emitted another items, and this gatherer in such case works incorrectly because it should only return the first matching value, but it returns all, unfortunately. So in the just remember as a rule of thumb, if you prematurely terminate the stream, you shouldn't use the greedy integrator in such case. Okay, nice. It wouldn't be so interesting if we are just talking about stateless gatherers, because usually the most powerful things are being employed when we are able to use the state of the gatherer inside it. How does it look like? If we want to talk about it, we need to somehow slide back to the diagram, because as you can see, in our gatherer, non-parallel one, because on today's talk I'm not talking about parallel gatherers because it's another story and would consume next half of an hour of that. So in non-parallel gatherers, we can also employ two another things. If you want to have a state in the gatherer, we need to somehow prepare it until before the first element is being pushed from the upstream. And this part that allows us to prepare the state is initializer. Initializer is the optional one, but if it is implemented, it allows us to prepare the state. And then this state is being pushed to the integrator along every item, and it can be mutated to manipulate the state of the integrator, and due to the state we can emit or not any different items. You can also notice that only when we are talking about stateful gatherers with the state inside it, we can somehow manipulate with the numbers of emitted elements, and with the state the numbers of emitted elements can be completely independent of the number of items being pushed inside from the upstream. So it's the relatively most powerful tool, and we will try to somehow present it in the next example. So let's go to our state, okay, finishers, okay. Oh, okay. I remember I forgot to add this slide with the stateful gatherers, but just forget me about it. So let's go to our part, and let's go here to our next slide, and it's 07. And this is distinct by selector. And this is exactly what we begin with at the talk. So we want to somehow select only cars with the distinct color, and we want to somehow use the key selector in this gatherer and decide basing on this key whether these items should be emitted or not. So how does requirement can be implemented using gatherers? Definitely, this is the case when we unavoidably need to use some state in the gatherer, because only basing on its state we can decide whether we are emitting this item or not, and it somehow should keep the history. And the solution is very simple, because in our case, this state should be just a set of the keys that has been already emitted. In our case, it would be just the colors of the cars, but I tried to implement this gatherer more or less generically, so we are not focusing only on cars and colors, but we are just using generic types T and P. T stands for the item that is being emitted in the gatherer. P is the element, the type of the key that would be extracted for each element if this stream that is being passed along this gatherer. Okay, and of course the intermediate state of this gatherer is as a set of p-values, and it's being stayed in this case. So what we need to do when we want to use this state? Of course, we need to prepare an initializer, and the initializer is very simple. It's just the supplier of this set of P, and in our case, it's just constructing a new instance of a hash set. The beginning is, of course, is empty because no colors have been already emitted, so we can just use this hash set and put the colors inside it. Then our integrator starts the interesting part. So in case of our integrator, of course, we are using of greedy because we need to consume each element of the string. We cannot just prematurely say, okay, we do not accept anymore, because you cannot exclude, for example, that the last element will still have the different colors than has been emitted already. So in such case, we are just using this selector function. It's also being passed as a argument property of this gatherer. And in such case, we are just, this would be the key extractor. And now we are using this function. We are extracting, in our case, the color, and then check whether if our set, the color is already present. If yes, we are just returning true and going to the next element. If not, we need to add this color to the set. So restore it and do not accept any other colors with this color. And in such case, because it's for the first time the color is being spot, we are just pushing this item downstream. Now, with all these implementations, using this gatherer is pretty straightforward. We are just constructing the new instance, pass the selector here, sorry for that, and we are just using this function. And now, if you run this code, as you can see, only 3 cars are being accepted. The last one with the black color is omitted, so the gatherer works exactly that way. The last part I would like to talk with these presentations is the part of this finisher, because why this can be used? What's the purpose of the finisher if non-parallel gatherers? Because okay, we are just having the state initializer, we are just emitting the elements, but why is the finisher? And it comes from the fact that in certain scenarios, we can emit the item only if we are pretty sure that we have consumed and processed through our business logic every items in the stream, because only after that we can decide whether to emit some elements or not, or do some additional actions at the end of the stream. And the example I would like to present with this finisher, it's just our, it's our example of max by selector. We would try to find a max element, but not basing on comparisons on just the element, but comparing these elements by some selector. And in our case, we will try to find a longest word in the stream and just emit in the gatherer. So in such case, we cannot be 100% sure which element is the longest one until we process all of them. So we need to somehow, of course, store the intermediate state. Probably it would be the longest word at this point. And then after passing through all these elements, we are able to emit it. So in our gatherer, we will just store the reference to the longest word in the atomic reference, because it's the simple way to make some mutable reference to some objects in such case. And at the beginning, we are just storing only null in this, so nothing is being stored. Then when our integrator comes into play, we are just using this function. We are checking whether the state is null. If yes, this is the first element, so we are just putting the first one. And then, if not, it means that it is already the second one element and so on. We are just trying to compare the current max value and the value of the item by this extractor apply. Comparing, if the comparison is positive, we are just putting the new element into state and return true. However, take into consideration that none of these operations in the integrator relatively emits an element because we are only manipulating the state and extracting the keys, but nothing is being emitted. The main part of emitting the max element is the finisher part, and as you can see, finisher part is a lambda that accepts two arguments. The first one is the state, and this state at this stage it contains the longest word, and the second is downstream. So I'm just pushing it to the downstream the longest word, and it's fine what we want to achieve. If we run this code, we should get this element kota. So sorry, it should be in English, but I presented it in Polish from the quick, but it means that Ella has a cat, more or less. Okay, let's go to our presentation because it's at the time is more or less up. So in such case, do gatherers have some weaknesses? Yes, they have. The first one is that they have no support for primitive types, and the second one, unfortunately, they do not have access to stream characteristic. It's more or less the same with the case of collectors because gatherers API borrows a lot from them and also shares the weaknesses with them. So unfortunately, this is the part I would like to say. And if yes, okay, if you want to try this code at home, you can just clone my repository. I would encourage you to do that because it definitely is a fine part. So I prepared the QR code to scan. So let me stay a little bit for a while. And after that, do we have any questions? Let's go to the wall Slido. Okay. I do not see any. No? No questions. Okay, that's fine. So thank you very much and have a good day of the rest of the conference and also tomorrow. Thank you.